Okay, a couple of things before we jump in here. One, if I could draw your attention to the following. This, I mean, you can always look this stuff up. If you're, if this is your first semester as a student at Cedarville, literally you just type in Cedarville University final exam schedule, and this will pop up, okay? So this exam schedule is sort of messed up this semester because of the abbreviated timetable. Although if this is your first semester in college, first, I'm sorry that it is, given everything that's going on. But secondly, the exam schedule is sort of weird. There are some finals that are happening on like Thursday, correct? And then there's nothing happening Friday. Friday's like a normal class day. But then Monday and Tuesday are the other exam days. And the other thing I will say is that it is literally impossible unless some professor starts messing with their exam time, which I would never do, that you would have two finals at the same time. It just would not happen. Does that make sense? So for instance, like, for us, we're Monday through Friday at 11, right? So you go in this row. And so the final's Monday from 10 to 11:50. Does that make sense? Now, there's some question as to whether that's even going to work, right? Oh, and by the way, since in theory, we also meet on Tuesday and Thursday, we would have the option of this one. Well, on Thursday, right? But we're not going to do that, okay? So what we do is we go with this one, yeah? So that's the plan. Now, whether or not we're actually going to take that live in person is another question, right? We're just going to have to see what happens. Things don't look good right now. We'll talk about that more later, okay? We're just kind of hanging on for dear life right now, so let's just keep doing that together. Any questions on that? Any questions? Well, let's talk about projectile motion a little bit, okay? I said we were going to do that last time. Now, remember that we have these vector valued functions that we can think of as position functions, yeah? We take the space curve generated by a vector valued function, and then we say, all right, as we move along that curve, as t increases, we think of that as time, and we can think of sort of the vector heads that form the space curve itself as a particle moving along that curve. In time. And then we notice that the derivative is really like a velocity vector for movement of that particle, right? It's kind of telling us about current movement. How am I moving currently? Then if we look at the rate of change of the velocity vector, the rate of change of the velocity vector, that's the derivative of velocity. That's kind of telling us how the velocity is changing over time. How would that be? All right, so the second derivative would kind of encapsulate that, yes? And the second derivative we've often called acceleration. So what's really going on here is acceleration is giving us a peek into the future. It's giving us a peek into how our velocity is going to change shortly, yes? So you have position, which is the original function. You have velocity, which is the derivative, yes? And you have these tangent vectors, which show you about current movement trends. And then you have acceleration, which is the second derivative that tells you about what's about to happen, yeah? You have these forces kind of working on things. So like acceleration is applying force in some way, and then the particle is responding to that, yes? So for instance, if the acceleration vector is pulling with the current velocity trend, then you would expect to see the velocity continue to increase. Does that make sense? The velocity would increase because, you know, the acceleration is saying, go faster, go faster. It's kind of pulling it along. And then the velocity vector would increase, and it might even turn in accordance with what the acceleration vector is doing, yeah? Now, if the acceleration and the velocity are perpendicular, then the speed is not going to change, okay? But the direction could. In fact, this example that we had right here was exactly that. Let's see, where was this? It was right here. This example right here, you recall? Okay, the red is the velocity vector at a given point, and the green is the acceleration vector. And all the acceleration is doing right now, because they're perpendicular, the acceleration vector isn't helping or hurting, yes? And by the way, do you remember what kind of a vector product told us about helping and hurting for two vectors thought of as forces? What was it? The dot product. The dot product was positive. So if the dot product of the velocity and the acceleration vector is positive, that means that you expect the velocity will be increasing moving forward, yes? The acceleration vector is actually dragging it faster, okay? In this case, notice, is the velocity vector changing? No. That is because the acceleration is just simply perpendicular to that. So it's not really helping or hurting as far as speed goes. But it is changing the direction, yes? It's changing the direction. It's saying, go this way, go this way, right? And so that thing's going and kind of turning like that, right? Okay? Does that kind of make sense? So, and by the way, if the acceleration vector was ever hurting our, you know, our velocity, you would expect to see the velocity vector shrink over time, like the speed would shrink over time, yeah? Okay, so that's just something I wanted to point out, okay? Any questions on that? That's just kind of a summary of what we were talking about last time. Position, velocity's first derivative, acceleration second derivative. Velocity is more about describing current movement patterns. Acceleration is more about future movement patterns. Yeah? Any questions on that? I'm sure that this is all like old hat from physics, but if not, I mean, we're at least talking about the interrelationship between these three without necessarily assuming that you're well familiar with these things. Okay, so let's talk about projectile motion. Okay, gravity is the only force acting on the projective after it's launched. Okay, we're going to think about this. We're going to think about this in two-dimensional space, just because it's easier to think about in two-dimensional space. Although we could have the same discussion in three-dimensional space if we were so inclined. Okay. So initial height here, we'll call that h, just for reference. That's the initial height that this projectile is launched. Okay. A lot of times, you know, we have like an angle also that this thing is launched at, okay, that we're concerned with. We have an initial velocity, okay, that this thing is launched at. And that's v of 0, okay, that's the initial velocity. By the way, v of 0 is the same thing as r prime of 0, right? It's the derivative of the position function, right? So this is the function r of t. Of course, v of t is r prime of t, and a of t, acceleration, is the second derivative of position, yeah? Okay. So r prime of 0 is the initial velocity. Now, what do you know about a of t? What do you know about a of t? What is that all the time? It's just gravity, yes? If you're a projectile, a of t is just gravity all the time. So actually that vector is going to be quite simple. Okay? It's going to be quite simple to deal with, okay? So a of t, we could actually write down what a of t is. It's just always It's always the same thing, right? It's just the acceleration due to gravity every single time, okay? Actually, this one, I shouldn't have drawn it down so far. It just goes down to that arrow right there. It's the same vector every single time acting on the projectile, yeah? Okay? And look, think about this. If the projectile gets to around like this, it gets over this, you know, this maximum point, starts to come down like this, suddenly your velocity vectors and your acceleration vector are helping one another, yes? The acceleration is actually helping the velocity along, yes? And therefore, what do you expect to happen to the projectile once you get over that hump? It's going to speed up, yeah? It will speed up until it reaches something called terminal velocity. But we're going to kind of ignore that for the sake of building this model. By the way, at this point, before I get over that hump, your velocity vectors point this way and your acceleration vector points down. Those two things are hurting each other, and therefore, what do you expect is going to happen with your speed? It's going to slow down. It's going to slow down until you kind of get over that hump, yeah? Okay. All right, so what I want to do is I want to derive kind of the projectile vector valued function. So remember, we know that a of t, which is acceleration, is the second derivative of our position function. And what is this going to be? Well, it goes straight down. We're doing this in 2 dimensions, so that means there's no movement in the x direction. And how much movement is there in the y direction? Look, we're going to let g equal to the acceleration due to gravity. Okay, g, I mean, sometimes typical units that you use are like meters per second. Meters per second squared is what you will use. Sometimes you use, you know, feet per second. Yeah, do you know what the acceleration due to gravity? It's like 32 feet per second, or 9.8 meters per second, right? And again, physicists always say meters per second squared, right? So that means for every second that goes by, the acceleration due to gravity is going to, and if you had a particle moving in the same direction as gravity, for every second that goes by, the velocity would increase by 9.8 more meters per second, yeah? So if it started at 0, after 1 second, it would be 9.8. After 2 seconds, it would be 19.6, etc. Yeah? So what you do here is you say, and by the way, you think of this thing as being positive, okay? So A of t is operating in a downward direction, so what are we going to say here? Yeah. Okay. And how would I get the velocity vector from this? Integrate. Yeah. Okay. So the velocity vector, okay, what we're going to do is we're going to integrate this bad boy. Okay. So it's going to be r, the integral of r prime prime of t dt. And we know that that means that we integrate each one of these things term by term, as we've discussed before. So it's going to be the integral of 0 dt, comma, the integral of negative g dt, okay? So the integral of 0, what sort of thing has an integral, or what sort of things has a derivative equal to 0? A constant, yeah? So we go like C1, okay? Negative g dt, what's up with that? Negative g t plus some kind of constant. Does that make sense? Like we could have different constants in the first and second coordinates, yes? So how in the world am I going to figure out what these constants are? Okay, C1 and C2, how are we going to figure out those things? Again, this is the formula for our velocity vector at time t, which by the way is also r prime of t, the derivative of position, okay? How would I figure out what those constants are? How would we figure that out? What do you think? Let's look back at this picture real quick, okay? Okay, so this is our initial velocity right here, correct? Okay. This is our initial velocity right here, okay? How could I get, like, so, you know, what we probably need to do is sort of figure out, okay, what are the coordinates of this thing for this initial velocity? What are the coordinates of this thing? Yeah. And maybe what we should do is like call this angle right, because this is going to be a right triangle, correct? I need to figure out like what the X and the Y coordinates are. Yeah. Let's call this angle right here theta. And by the way, theta would be the angle between the initial velocity vector and I. Does that make sense? That angle right there would be the angle between that vector and the vector I, which is just the vector 1, 0. Yeah? How could I figure this thing out? The way the book kind of uses a script V0 for the length of the velocity at time 0. Okay? And you know that this thing right here has length V0, yes? So the length of the hypotenuse is V0. How could I figure out the coordinates for this vector? What trig functions would I use? What's that? Cosine and sine, yes? That side right there, the horizontal side, we would use cosine, correct? Again, this is a right triangle. You would use cosine. Okay, you would say that, or a cosine of theta is equal to that side over V0, yes? So that side is equal to V0 cosine of theta. Yeah, we've done this kind of trick before. So that side right there is going to be V0 cosine of theta. Don't you see? Yeah? And what about this thing right here? What would that be? V0 sine of theta. Okay? And again, script V0 is just the length of the velocity vector, yes? So what does that tell us about the original velocity vector? Okay, so V of 0. Okay, V of 0. The coordinates are V0 cosine of theta, comma, V0 sine of theta. Okay? Does that make sense so far? We're going to kind of utilize that here in just a second. I just want to make sure that that makes sense to you. Okay? Let's go back over here to our kind of derivation of this thing. Okay? So this vector right here, by the way, I don't want to lose track of what we were doing, but this vector right here, that is the initial velocity vector. Okay? Okay, the initial velocity vector is equal to that. Okay? So let me ask you a question. How does that help me determine the constant? Or how does that help me determine these constants? Yeah, that's right. So that angle theta, by the way, that was the initial launch angle. That's not something that like changes. Does that make sense? Yeah. So if I plug in, I mean, look at this right here. V of 0 is equal to those things, right? V of 0 is equal to these things. So look, I'm going to erase this acceleration due to gravity thing right here. And I'm going to write in here this is also equal to, look, if I plug in 0 for t, down here, that's got to be C1, comma, negative, or sorry, do I even have, I'll just write it, negative g times 0, which obviously is 0, excuse me, yeah, plus C2. Okay, so what is C1 and C2? Well, C1 is V0 cosine of theta, and C2 is going to be V0 sine of theta. Okay, so let's write that down. So this is equal to V0 cosine of theta, comma, negative GT plus V0 sine of theta. Okay, so far so good. That is our velocity. That is our velocity vector, correct? Okay, what are we going to do next? If our goal was to find r of t, the position function for this thing, what are we going to do next? Integrate again. So here's what I want you to do. Okay, I want you to kind of think about it on your own, like with someone next to you or something, okay? So think about it on your, think about what you're going to do next to try to pull this off. Does that make sense? Okay, think about what happens when you have to integrate these things again. And remember, you're not, okay, be careful, you're not integrating with respect to theta, yeah? Cosine of theta, that is a constant, yes? Sine of theta, that is a constant. So it's like that V0 thing. That was just the initial kind of launch angle and initial velocity, yeah? Okay, so please do think through what would happen next with this to get back to the position function. So talk about that with someone nearby. Seems like there was some good discussion going on. Help me out here. So what are you going to do to find r of t? That's right, we're going to integrate. So if I integrate the first coordinate, we're going to integrate what, Michael? Yeah, with respect to t. And remember, that's a constant. This is a constant in t, yeah? That's just a stinking constant, right? So what do you get? So that's constant in t. So what do you get in that first coordinate when you do that? Yeah, so V0 cosine of theta all times t plus some kind of constant, yeah? Okay. Look, I'm going to use a different letter for the constants. I already used C1 once before. I'm going to say that I'm going to call this K1, okay? All right, just for a constant. In fact, I'm not even going to use script K because I don't want you to think I'm talking about a vector or something, okay? So plus K1, comma, what's the second coordinate going to be? What's the second coordinate going to be? Right, negative 1/2 GT squared plus V0 sine of theta times t plus what? Plus K2, all right? Again, you just treat V0 sine of theta like it's a constant because it is. And G is also a constant, okay? Now, how do I figure out what, okay, so what's the next question? How do I figure out what? How do I figure out these constants? I have a couple constants right here again. What are we gonna do? What do you guys think? Remember H was our initial height? Remember that? So what is that going to be? R of what? Yeah. R of 0, that's like our initial point on that curve, yeah? Okay, so the initial height is R of 0. So isn't that going to help us kind of figure out what this thing is? Let me sort of erase this little piece over here. I think we basically have this in our cognition at this point, hopefully. Okay, so R0 gives us that, right? So by the way, what is R of 0? Think about it. What is the initial, well, okay, that is the initial height, okay? So let me just say that implies, it doesn't equal that. That implies that R of 0 is equal to, what are the initial coordinates of R0? Because this is a vector, I can't call this isn't a number, right? So what is that, what are the coordinates of the initial thing then? What's the x coordinate? Since we sort of think of the projectile as launching off of the y-axis, right? Sort of thought of that thing launching off of the y-axis. The initial x coordinate is 0. And what's the initial y coordinate? H. See what I'm saying? Okay. Therefore, if I plug in t equal to 0, what do I see that K1 would have to be? Think about it. I know that R of 0 is 0, comma H. But like R of 0 here, hang on a second. Let me just write this down here. Look, R of 0 here, if I plug things in, I just get K1, comma what? K2. Yes? But you know that that has to be 0, comma H. So what does that tell you about K1 and K2? K1 is 0, K2 is H. Therefore, we get our position function. The position function is V0, which is the initial velocity, cosine of theta, t, that's it. And then the y coordinate is -1/2 gt squared plus initial velocity, sine of theta, t plus what? Plus h. Look at that. That is just, I mean, I don't know. I'm going to feel pretty good about myself for the rest of the day after sort of coming up with that, right? So that's the actual formula for the projectile motion. Okay, some of you have seen that before. Notice that like the x coordinate simply just moves along linearly in t, yeah? The x coordinate just sort of moves along linearly in t. The y coordinate, there's a lot more action happening. It obeys kind of like this parabolic trajectory, which kind of makes sense when you think about it. Okay, I think that's pretty neat. Some of you seen this, something like this formula before, maybe. Okay, well, this is the formula for projectile motion. I think I have it right here. Okay. Let me erase some of this. Any questions on this before we move on? Questions about the computation itself? Essentially, all we did was integrate twice. And we thought about initial velocity and we thought about initial height. And those two pieces of information combined led us to this formula after integrating 2 times. Okay, so now you've seen why integration of vector valued functions is actually a useful tool indeed. Okay, but the formula itself is right here. Okay, doesn't that exactly comport with what we just had? V0 cosine of theta times t, I, right? So that means that's the first coordinate. And we have h plus V0 sine theta, t minus 1/2 gt squared. Yeah? I think that's pretty cool. I want you to, if you would, kind of work on this little problem on your own. This is an application of this. Quarterback of a football team releases a pass, height of 7 feet above the playing field, and the football is caught by a receiver 30 yards directly downfield at a height of 4 feet. The pass is released at an angle of 35 degrees with the horizontal. And the question is to find an equation for the position of the football at time t. Now remember, the acceleration due to gravity, in this case, what do you think we would want? Yeah, so this is maybe feet per second squared. So let's do 32 feet per second squared, okay? That's what the acceleration due to gravity would be in this case. Of course, 30 yards would have to be converted to feet, right? And presumably, yes, okay? But I want you to come up with an equation for the position of the football at time t. And I also want you to find the speed when the football is released. That would be sort of the initial velocity's magnitude, yeah? So think about this together for a few minutes, okay? All right, here. Hang on a sec. Okay, let's do a little, let's go to a whiteboard here and we'll kind of talk this through. So does somebody want to talk me through the process here? First of all, what's the formula for our R of t generally? I mean, just who cares about what all of the specific things were necessarily at first? But what was the formula we came up with? Initial speed, cosine of theta, t, comma, yeah? And then what was it? Negative. Uh-huh. Well, sine of theta, right? T plus h, yeah? And we have some specific information we know here. For instance, we're going to work with g equal to 32 feet per second, yeah? Feet per second squared, yeah? Okay. And what about h? What was the initial height? 7 feet. Okay, what else do we know? The angle with the horizontal, what was that? Yeah, 35 degrees. We just have to be consistent with how we think about this, yes? Okay. And so, I mean, we could write this, we could at least kind of fill in some of these details. So R of t equals to V0, which is the initial speed, cosine of 35 degrees, t, comma. Okay, so since g is 32, negative 1/2, so what's that going to be? Negative 16t squared plus V0 sine of 35 degrees, t plus 7. Okay, now what? So we at least have a formula written down, but there's something kind of missing here so far, right? I mean, we still don't know what the initial speed is, correct? How can we sort that out? How can we sort that out? Okay, so Maria's saying, just think about X and Y separately. Okay, so how's that going to help, Maria? Uh-huh. Okay, so are you going to work primarily with X or with Y or with both? Okay. So what you did is you said, okay, so like you think of 0 as being the initial time, correct? But then there's some time in the future where the X coordinate kind of stops. It's where the pass is caught, correct? Okay. So then what did you do? So you said like V0 cosine of 35 degrees, okay, times t final or something, yeah? Right, because t final, just so we're clear, t final is the time that the pass is what? Is caught. Okay, so you're saying that that is what? 90 feet. Okay, so the x coordinate has changed from like 0. You think of that as being like, you know, the place where this whole thing all started, and the ball has traveled a total of 90 feet horizontally. Yes? Okay, and then what else did you have? Yeah, so negative 16 t final squared plus V0 sine of 35 degrees, whatever that is, times t final, plus 7 equals, right? You know that the pass is caught at what height above the ground? Remember, this is the x coordinate right here, and this is the y coordinate right here, yes? Okay. So at that final moment, when the pass is caught, what is the height? What's the height? 4. Okay. And then what's your suggestion, Maria? How can you sort this out now? Yeah, okay, yeah, that's a good idea. Let's, instead of calling this T final, let's just say T, this is T sub big F, yes? Okay, so you can kind of use this equation to say that TF is equal to what? 90 over V0 cosine of 35 degrees or something, yeah? Okay, and then what do you do? What do you do with TF? You plug it in. So you take that thing, you put it right here, and you put it right there. And then what will be the only unknown once you do that? V0. So once, let me just kind of say this since we're running out of time. Once we plug in TF, V0 is the only unknown. Solve. Yeah? Solve, and what do I mean by solve? Solve for V0, the initial speed, yes? The magnitude of the initial velocity vector. Were you able to kind of get that thing worked out? 19.05? V0 is equal to 19.05 what? Okay, 19.05 feet per second. That's probably, that sounds reasonable to me. Okay, cool. That's it.